All right, let's start. Let me see if the recording is properly set up. Oh, okay. Okay, let's start. So before we actually start today's lecture, let's quickly have a look at what's next. So this week is actually week 9, is the second last week for this term. And actually it's towards the end of this course. And we will be learning some advanced algorithms for doing testing in this week. And these algorithms might be not only useful for testing, but it could also be applied to some other scenarios. And and in our next week, we will only have one lecture on Wednesday, which is a recap of the entire course. So it's like we don't have final exams, but it's good for you to have a recap or to have a systematic view of what you have learned this term. So you could see that everything you have learned in this course for this term is kind of connected to each other. So this is roughly our plan. And okay, let's continue to today's main content. So today we are going to learn some advanced algorithms in testing. And this is today's outline. So before we actually learn these algorithms, let's try to formulate testing as a search or optimization problem. And then because we can formulate testing as some kind of problem, then we can apply some algorithms for solving that type of problem, right? So this is what we are going to learn today. And first, let's have a revisit of how do we create test cases. So we have learned that software testing is basically to generate some inputs to try the program with the inputs we have generated and see what happens, right? So this is essentially what testing does. However, when we generate these inputs, we don't just try any input, right? Because it's not very effective. So instead of just trying some inputs randomly, we have some purpose, right? We could have different purposes here. And we want the test cases to be able to find some faults, right? That's the most fundamental thing we want to do with testing, right? And we may also want to observe to obtain some coverage over some structural elements of the code. For example, the statements, branches, or even a path. So this could serve as an evidence of how much of testing effort have we done, right? So we have some purposes here, and we may also want to create different combinations of representative values, right? This is kind of related to how we create test cases for equivalent class testing or combinatorial testing, right? So we have different purposes here. Or if we use data flow information, we may want to execute all the def use pairs. So we have different purposes here instead of just generating the inputs without any purpose randomly, right? So we have different purposes, but what does all these have in common? So let's think about this problem. So do we have a goal when we do testing? We do, right? Although the goal could be different, we do have a goal when we do testing. We want to find more bugs. We want to obtain some kind of coverage, achieve a certain level of coverage, right? We do have a goal. And the second thing we want to think about here is, can this goal be measured? For most of the goals, the answer is yes, right? Because we can measure the number of faults we have found. We can measure the level of coverage. We can count how many pairs of the combinations did we cover, right? So we can measure the goals here. Then, because both of the answers are yes here, then we are like kind of searching for a desired test suite. So why this is like searching for such a test suite? We can describe the problem again in this way. So we know that the input space is almost infinite, right? We can give a program any random input. It's just that the program may refuse to take our input, but we can supply any input. We can give any input to the program. So out of the near infinite set of inputs, we would like to have a set of inputs that can obey certain properties, that can cover some structures in the program, that can try out all the combinations, right? We do have some goals here. So it's like we are searching for such set of inputs that can satisfy all these different goals from a huge input space. So it's like we are finding something, we are finding a suitable thing in a big space. So testing could be described as a search problem, like we are searching for a suitable test suite. So this is the idea here. And let's continue to explore this kind of theory of thinking testing as a testing problem. So we have learned that it's actually impossible to justify that we have found all faults or all bugs in a particular program, because it's like the program space is infinite, and the requirements could be changing, right? The environment of running this program could be changing. So we can hardly say that a certain program is free of bugs. So we know that, okay, this final goal couldn't be checked, but the testing goals we just mentioned, all of them could be measured somehow, right? We can measure how many faults we find. We can't say we have found all faults, but we can count how many faults we have found, right? So we can measure all these testing goals. For the Boolean goals, it's just whether a certain property is satisfied or not, like certain level, like for example, have we tried all the possible combinations of different options, right? So this is like a Boolean goal, and we do have numeric goals, like what is the percentage of coverage we have achieved for this program. So we can measure all these goals, and if we can take a certain test suite and check whether this test suite or this solution of this searching problem meets our goal, then we can write programs to automatically search for this solution, right? So in this way, because we can convert testing as into a problem of searching for a suitable test suite, and this searching problem the goal of this searching problem is measurable, and we can generate the candidate solutions automatically. Then we can use a program to automate everything here, right? So actually, most of the searching-based testing techniques are kind of fully automated. So it's like we can use a program to fully automatically generate test cases. And here is a typical searching process. So it's very, very simple actually. So we just randomly choose, or we use some strategies to choose a solution. And if this solution is not satisfactory, then we just try another solution. And we keep on trying these new solutions until we achieve our goal or we tried out all the possible solutions. So as you can see here, we are choosing solutions one by one when we are and try to check whether they could help us to achieve the goal. Then the order of selecting the solutions to try is important here, right? It could affect the efficiency of finding this final solution here. So this requires actually some strategies to deal with. So actually a searching problem requires some strategies for us to make such decisions like which solution to try out next. And these kind of strategies we are using here to make these decisions are kind of called a heuristic. So heuristics are actually used for like choosing these solutions or ignoring some of the solutions. And talking about strategy and heuristic, let's think about this problem here, which is a live poll. So I don't know if you have if you have went through the assignment 2 specifications, but if you have done so, you may notice that in assignment 2.2, feature 2, we try to implement a seed prioritization strategy, which is a strategy for prioritizing which seed should we select next when we generate new test cases, right? So it's about the ordering of selecting seeds to try out. So we know that the order that solutions are tried is important for improving the efficiency. So the question here is, does this strategy or this heuristic we use for seed prioritization affect the final coverage after converging? So if you wonder what is converging, converging means that, so you can see that the y-axis here is actually the code coverage, and the x-axis is the time we do testing or fuzzing. So you can see that after a certain time, the coverage doesn't grow. So it means that this algorithm of testing has converged. So converging means it's reaching its maximum capacity of this algorithm. So do you think that the strategy of which of um, the strategy of the ordering of how we try out different seeds could affect the final performance after convergence? So yes or no? So you can just make a guess. Yes or no? So you just feel free to make a guess, and let's see the result. Actually, most of you have chosen yes, but the correct answer is actually no. So let me explain why it is no. So before we before I answer why it is no, we need to make clear two concepts here. So the first one is efficiency, and the second one is effectiveness. So efficiency and effectiveness are actually different in the context of testing. So efficiency means how fast we can do things, right? And effectiveness means how well we can do these things. So efficiency here in testing, it means the convergence is related to the convergence speed, and effectiveness is related to the final performance after convergence. And actually, because seed prioritization is only dealing with which one to try first, but it doesn't affect whether we should try something or not, right? So it only affects the ordering, but it doesn't affect whether we should try something. So it doesn't matter if we try the good seeds or good test cases first, then we can converge faster, right? The coverage will grow faster. But eventually we will try all the seeds given enough time, right? So it doesn't matter. So because given enough time, we can try out everything. It doesn't matter in which order did we try these things, right? So so the ordering of trying out different solutions doesn't really affect the final performance. So it only affects how fast we can reach an optimal solution here. So seed prioritization doesn't affect the coverage after converging. And talking about heuristics, there are some heuristics we have encountered actually before when we learn some other algorithms. So for example, so we know that, okay, heuristics are the uh, decisions or strategies we use to choose certain solutions or ignore some solutions. So let's think about the problem of searching in a graph. So you might have learned some algorithms of doing graph search, right? So if we arrange some nodes in a hierarchy, and then we can apply BFS, which is to try out a graph by level. So we try to exhaustively test all the nodes, visit all the nodes on certain level, and then we move on to the next level. So this is BFS. And we could also try out DFS, which is to explore the graph by trying out the deepest node first, and then do backtracking, right? So we can use different strategies here. And these strategies are actually kind of like some searching heuristics here. And these are some very naive but easy to understand and implement strategies. And we could also have some more advanced strategies when we do searching. We could do A star searching. So, which is actually a greedy algorithm. So we can attempt to estimate a shortest path to our final goal. And then this 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 shortest here could be estimated using different definition. We could estimate the time of reaching the final goal. We can use the distance towards the final target, right? And then we examine all the next moves we can take and see which one will get us to the make us closest to the goal according to the definition of shortest here, right? So this is a greedy algorithm because we only check the next move. And however, as you could see, this requires the light is turning off again. So and actually, this because we need to know which one is leading us to is getting us closer to the goal, right? So we need to define this term of closer here, and we may need some domain-specific scoring function to check the distance. And this domain-specific scoring function is actually a heuristic we are using here. So price first, the price here is the heuristic, depth is the heuristic, and this domain-specific scoring function is the heuristic here we are taking. It's like some kind of strategy or some kind of assumptions we make that could affect our decision making. So this is heuristic. And talking about searching, let's come back to the searching and testing. So previously, there was a workshop in a famous software engineering conference, which is called search-based software testing, and it's actually a workshop plus a competition. So, but now it turned into search-based and fuzz testing. So it actually it means that we can see that fuzzing is actually getting very, very popular now. So that's why we choose it to be the topic of your assignment too. And you can see that search-based testing is actually a very, very popular topic in the field of software engineering. And let's learn about some other key concepts in search-based testing. So when we talk about some any algorithm, we need to think about the budget we have or the cost incurred by the algorithm. So the desired case or the ideal scenario is that given a testing problem is that we should try all the possible solutions. But this is desire, but this is not achievable, right? So because we know that the input space is kind of infinite, so we cannot try all the solutions without constraining the problem. So if we don't apply some constraints, we cannot there could be infinite number of solutions we can try. But if we somehow can apply some constraints, then we can limit the number of solutions to try, right? So this is the idea here. And this leads us to the idea of bounding the searching problem with some kind of search budget. And this budget could be in the form of the number of attempts we have tried. So we can limit the number of test cases or the number of solutions we are going to try. And we can also limit the budget by time. So we can say that, okay, we just want to run this fuzzing process, for example, by 5 hours. Or so this is one type of budget, right? And the other type of budget is that we can say, okay, when we run fuzz testing, we just want to execute the target program like 10,000 times, right? Then this is another type of budget. So we can use either one of them as our search budget here. And this search budget is actually serving as the constraint here. So basically the idea of the algorithm we are going to learn is to try to find a suitable solution before the budget expires. So in this way, we can actually further convert the problem here. So we know that sometimes true and false goals could be hard to solve under a budget. So because if we want to say, because let's say we try to run fuzzing for maybe 1 hour on a particular program, and we didn't find any bug. Can we say that this program is free from bugs? It's no, we can't say that, right? Because we don't know what will happen if we continue to run the testing, right? So true or false goals here, like whether this program is free from bugs, is actually hard to answer because of the budget, because we don't know what will happen if we give this technique more budget. So we may get the answer of unknown if we can't find the satisfying solution here. So we can try to use some measurable goals to convert this searching problem into an optimization problem. So instead of searching for a good or satisfying solution, what we want to do is instead of searching for a very good solution or satisfying solution, what we want is we can optimize. We can try to find a satisfying or the best solution within the budget or among all the candidate solutions we can get within the budget. So this is the idea. So instead of finding the most ideal solution or the final solution, because we now have a budget, right? So we can just get a partial solution. So for example, instead of having the best test suite we can get for a particular program, what we can do with a budget, under a budget is we can get the test suite that can obtain the highest some kind of coverage among all the candidates we can get within the budget. So we are getting the optimal solution here rather than the best solution here. So we can actually, if we apply some limits or constraints or budgets, then we can transform these kind of searching problems into some kind of optimization problems. So the the saying here that of searching for the best possible solution given a budget is kind of an optimization problem. It's kind of like how we describe optimization problems. So this is actually also similar to the concept of local versus global optimal. So for searching, we are kind of looking for the global optimal, right? So we are looking for the best solution. But for optimization, since we have some limit, so what we can get is the best solution out of all the candidates we can have in this within the budget, right? So for optimization problem, we are kind of looking for some partial solutions or local optimal here. So now we can rethink about the problem of how could we convert testing as an optimization problem. So just now we learned that we are, instead of searching for the globally best solution, we are searching for the best solution possible among all the candidates that we can get within the budget. So this is the optimization problem we get here. And therefore, because we are having some kind of budgets or constraints here, right? So we don't have infinite resource for us to find the solutions, to try out different solutions, then the searching heuristic becomes important. So if we use time as the budget here, then the time we are taking to create, execute, and evaluate a solution becomes important. And if we limit the budget, if we use the number of attempts as the budget here, then the strategy used to choose solutions, to select solutions is important. But in practice, we do want optimal solutions in both categories for the purpose of high efficiency. So there are actually many searching strategies here that we can try out, and we are going to learn two of them today. So next we will learn a searching strategy called adaptive random testing. So here let's think about the most naive or most simple form of searching, so that which is called random search. So what we do here with random search is that we just randomly formulate a solution. So this is very straightforward, right? So for in the context of testing, it could be like this. So for unit testing, assume that we are testing an object-oriented program. So what we can do is we can choose a class in the system as the unit we are trying to test, and then we can randomly generate a series of method calls of that class. And then we can randomly select the number of calls, right? We can select random methods to call, right? And then we can generate or supply random parameters to the methods we have selected, right? So everything is fully randomized. So for gray box fuzzing, we can also try out these random searching strategies. So for the seed prioritization problem, so which is related to which seed to use next, what we can do is we can randomly select the next seed, right? And this is a default implementation for assignment 2. You need to implement some advanced strategies. So we can, after getting a particular seed, then we need to determine how many new test cases we could generate from the seed, right? And this is called the power scheduling problem, right? So when dealing with this kind of power scheduling problem, we can randomly assign powers, right? We can randomly determine how many new test inputs should we generate with the given seed. So this is also random, and we can, of course, randomly mutate the seed to create new test cases. So we can do things fully randomly. And there are some advantages of doing this kind of random testing. It's actually also very, very popular, the full random testing, because it's very fast and it actually requires no planning at all because it's just pure random. And it's also very, very easy to implement. So you just need to write some random code generators. And it's easy to understand as well because everything is determined randomly. And one more hidden or sometimes likely to be ignored advantage of doing full random or pure random testing is that all the inputs here are considered equally. So there's no designer bias. So sometimes when we are trying to do testing, we try to apply some heuristics based on our experience, based on our assumptions or observations. And these observations or assumptions may not hold all the time. So this is considered as designer bias. So so we may so we may somehow avoid this kind of designer bias by doing things purely randomly. So randomness is actually not a bad thing. And when you do assignment 2.2, the feature 2, if you, because we are trying to use a priority queue for maintaining the seeds of the test case of the gray box fuzzer. So if if you just don't apply or don't select from the non-favored seeds, it is considered as a designer bias here. So you should avoid this. However, there are many drawbacks of random testing as well. So as we see that, okay, random testing is simple, it's fast, it could avoid designer bias, but it could also have many drawbacks. So let's see this example from this comic here. So you can see that, okay, this little monster tells us that, okay, over there we have a random number generator, and this random generator keeps telling 9. And then this guy asks, are you sure that's random? Okay, that's the problem. With randomness, you can never be sure. So the problem is, with randomness, we can never be sure. It lacks actually both efficiency and effectiveness most of the time if we do things purely randomly. So that's a problem here. So we need, although we could introduce designer bias, we still need some strategies and heuristics here. So let's think about this problem here and how could we design some heuristics So first, let's observe the input space of the programs. So this is like an illustration of the input space of programs. So the sunflower here denotes the text that could pass, and the ladybugs here denotes the test cases that would fail the program. So we can see from this illustration here that faults are actually sparse in the space of the input space. So this is because like when we like in when developers write programs, they are they won't make some very it's very unlikely that they are making some very simple mistakes, right? So most of the bugs or faults are corner cases, right? So the input for triggering these corner cases are actually very sparse in the input space. However, it could be dense in certain parts of the space, right, if they appear. Because, for example, when you implement some kind of program, there could be certain part of the program where the logic is very complex and the code could be very, very fragile, right? And in that part of the code, you could have a high density of bugs. So although the faults are very sparse, they could be very highly, they could have a high density in those fragile or vulnerable regions. And and if an input causes a failure, a similar input is also very likely to cause the same failure. So this is because they are very close to each other, right? It's very likely that they trigger the same fault. So these are some observations here. So we can have our assumptions and heuristics based on this observation here. So rather than what we want here is rather than choosing tests completely randomly, we favor input diversity. So the strategy here is if a test case does not meet a goal, then when we generate the next test case or the new input, we should try a very different input from the previous ones we have tried. So we can promote diversity here. So this is actually the most basic idea of adaptive random testing. So for example, if we have generated a test case like this, what we do is instead of selecting a seed, generate another test input that is close to the one we have tried before. So instead of we don't want to try this one because it's too similar to the one we have tried. So instead of trying this, we should randomly generate some other inputs which are further away from the unsatisfying input we have tried. So this is the basic idea, and this will this will be, you can see from this figure that it's more likely for us to find bugs if we try out more diverse inputs because that the bugs are kind of very sparse in the input space. So this is a basic idea, and there are some algorithms to implement this idea. So this algorithm here is called fixed size candidate set algorithm. So fixed size candidate set adaptive random testing. So this is a full name. So it actually makes use of two sets of test cases. And the first one is the executed set. So basically it keeps all the test cases we have tried. And then and these test cases must also not meet our previous goal. And the second set of test cases is the candidate side. So it's just a set of test cases that have been generated but not yet tried. So here are the key steps of this algorithm. So first, we generate a test and then execute the test, and then we generate the random. Sorry, we generate the candidate set, and then because we have executed this test, right? And if it doesn't meet our goal, we will choose from the candidate side the furthest test away from what we have executed, and then execute that candidate, and then put that candidate back into the executed side if it doesn't meet the goal. So this is very, very simple and straightforward. However, there are some decisions we need to make in this process, right? You could see that we need to choose the test which is furthest away from the executed tests. And how do we determine this distance here is a problem, right? So we need to have some strategies. And before we look into the details of the strategies, let's have a look at why this algorithm is needed here. Actually, it generates because we are only selecting the test cases. We can generate because here, as you can see in this step here, we generate n test cases. We generate a set of candidates, and we only select one to execute next. So you can see that we generate many more test cases than we execute the test cases, right? So more test cases are generated than executed. In random testing, all the test case we generate are executed. We don't have any strategies for determining which one to execute or not. So normally execution is more time consuming than generation. So executing a target test case is considered to be more time consuming than generating a new test case. So in theory, we could not, we could run these adaptive random testing faster, and because of two reasons. The first one is it can execute much faster because we are not executing as many test cases as random testing, right? And the second one is we are trying out some strategies that can promote the final diversity of our test suite. So these are the two reasons. And now let's come back to how should we deal with some of the decisions in this algorithm here. So to we need to choose that the key decision we are making here is to choose the next candidate for execution, right? And it is according to the distance, right? So we want to choose the candidate that is furthest away from what we have executed. And here we have actually two strategies of calculating the distance here. So the first one is called maxi-min method, and the second one is maxi-sum method. So maxi-min means we we use the distance between the closest the candidate is given a candidate test case. We use the distance between the closest distance between the candidate and one of the test cases in the executed tests as the distance here. So we only use the closest distance against the executed test as the distance of each candidate. And then we select the candidate with the largest distance. So this is the idea of maximum min. And the idea of maximum sum is that we use the sum, because in the executed tests, we have multiple test cases, right? We can use the sum of the distance between a candidate and each one of the test cases in the executed test set as the distance here of the candidate. So we can use either one of them to calculate, to determine which candidate is furthest away from the executed tests. So this is the first decision-making point. And the second one is, so now we know how could we determine which one is the furthest away, but we need to determine how far or what kind of measures do we use for measuring the distance, right? So we need to determine the distance here. And the distance could be determined according to the type of the candidate, or the value of the type of the value of the candidate. So for numeric values, we could use Euclidean distance. So the Euclidean distance is basically calculated like this. And for strings, we can use this kind of distance and many other distance calculation methods. And for different types of values, we can apply different distance calculation methods. And that's about adaptive random testing. And there are some variations of adaptive random testing which are kind of considered as improvements. So the first one, so the one we are going to learn here is zone-based algorithm. So what we do is we still the basic goal is still similar to adaptive random testing. We still want to get the most diverse test suite. And what we do here is we define we still use the concepts of distance here. So what we do is we define some exclusion zones. So these exclusion zones are like some bubbles surrounding the test cases that we have already executed but doesn't meet our goals. So as indicated by the name of the exclusion zone, so when we choose the next input to execute, we don't choose from those inputs which are within the exclusion zones. So you can see that this is a little bit different from the idea of adaptive random testing. In adaptive random testing, we are choosing the test case which is furthest away from the current test input, right? Which is definitely outside the exclusion zone, right? So, but here it doesn't. We just need to choose input out of these zones, and it doesn't require the candidate we choose doesn't require to be the furthest away. So this is a basic idea here. So this is roughly how it works. So initially we decide this exclusion zone to be of certain size, and then all the zones are of the same size. Then we shrink the size of the zones as more test cases are executed. So you can see when we initially maybe we are starting with the zones with a black or gray, dark gray color here. And the more test cases, so we don't select from within these larger circles, and then we just select randomly from the other places, the other spaces in the input space. But then after the more test cases we have tried, because we will have fewer choices, right? Because this entire input space will be very crowded. So we need to shrink the size of the exclusion zones the more test cases we try. So this is a basic idea. And another idea on top of this exclusion zone is called dynamic partitioning. So what we do is we break the input space into different regions, and then we choose a test from the largest unexplored region. So for example, now we have three different regions, right? And we have tried three different test inputs. So when we select the next one, we select from the largest region, which has not been explored before. So this can also help us to ensure the diversity of the test suites we can get. So this is roughly the idea. And the good thing about this dynamic partitioning is that because it actually also depends on how we do the partitioning here. So the good idea is that we are not starving any input because we it makes sure that at least one test input is selected from each region here. So because if we don't do this kind of partitioning and we just select randomly out of the exclusion zones, then we may we may end up in not covering certain regions, right? So because of the randomness, so we may end up in starving some of the regions. So if we do this kind of partitioning and select inputs according to the regions, then we can we can evenly spread our test cases across the input space. So this is the idea of dynamic partitioning here. And theoretically, these zone-based techniques are kind of better than the naive adaptive random testing. So that's all about the first half of today's lecture. And let's have a 10 minutes break, and I'll see you at 7 past 12. So for these algorithms, you don't need to really know every detail of these algorithms. You just need to know that the brief idea of how it works, and you know there is such a thing, and that's the basic idea. So these are some advanced algorithms. You don't have to really master them. You just need to know, okay, there's such a thing. And they are not only useful for testing, they could be useful for other problems. Like that's why we are trying to convert testing as some searching or optimization problem, because we can apply some general algorithms. So if we can transform the problem here. Okay, let's start the second half. So we are going to learn the genetic algorithm, which is an even more advanced algorithm for doing testing or creating test suites. So before we jump into the actual algorithm, let's revisit the problem of optimization. So normally there could be too many restrictions for us to exhaustively do the search, right? So that's why there's no way to try out all the inputs. And so we need to explore some strategies for sampling from the input space or selecting the test inputs. Uh, but this but this strategy shouldn't be purely random, right? So we should have some kind of strategies here. And the question is, so we can use some strategies to improve effectiveness and efficiency and to automate things, right? But the thing is, just now all the strategies or heuristics are kind of based on some of our observations or some empirical findings, right? So how can we kind of automatically select the best strategy here? Can we even automate the selection of strategies? And actually, this leads us to the meta heuristic searching techniques. So just now, sorry, all the algorithms we learned are kind of heuristic based algorithms. And now we are going to learn some meta heuristic techniques. And if you wonder, okay, what is a meta heuristic? It's like a heuristic for finding heuristics. So this is like, if you wonder what it means, we can use another example to explain this idea of meta heuristic. So for example, let's assume that we are trying to generate a constant or configuration setting. So the easiest way to do it is to use a preset value, right? We just fix the value. And the better way of doing it is actually to use a random number with a fixed seed to generate this random number. And an even better way of doing this is to use a random number that is seeded with the system time, which could be considered as a changing seed, right? And the best solution here is to use a random number generator to generate the seed for the random number generator. And this random number generator for generating the seed is actually considered the meta heuristic here. It's like the heuristic for heuristics. So it's basically to some meta heuristics that can help us to derive some other heuristics. So this is a basic idea. And the optimization problem here is if we can calculate if we can calculate a score for each of the testing goal, then under some constraints, then we can convert the problem into an optimization problem. And the score of that testing goal is like our optimization target. We want to maximize the score, right? So we can convert the test generation as an optimization problem here. So what we can do is we can generate a test. We can score each one of the tests with a fitness function here. So we can use some kind of function to assign scores to each one of the tests we have generated. And then we can manipulate the solution according to some kind of strategy. And this strategy here is the meta heuristic we are going to apply. So this leads us to the very basic idea of genetic algorithm actually. So as indicated by the name of this algorithm, is kind of inspired by some biology concepts. So the basic idea of this algorithm is that with multiple generations, we try to evolve a population of the targets. And then we favor the good targets or the targets are actually the solutions or the test cases here. So we favor the good solutions in each generation and filter out bad solutions in each generation. So this is the basic idea of genetic algorithm. And because just similar to the adaptive random testing, so we have to promote diversity of this population here. So that is to cover the corner cases to find the bugs. So diversity is introduced into the population of each generation here by keeping only some of the best solutions, but we don't keep, um, we may keep some. So this is the first step. So we keep the best solutions here because we are favoring these best solutions. So the diversity is introduced by randomly generating some population members. So we have a population size, but we don't fill the entire population size with the best members. We still randomly generate some new members in the population. And then we create offsprings through mutations, like we can randomly mutate the members of the population. So this gives us some diversity, right? And we can also try to do crossover by selecting some of the solutions in the population to generate new offsprings. So this is the basic idea here. So this is actually similar to what we are doing for example for the father. So basic idea is so this is it's a meme. So basically the idea is we have some best members in the population and then we generate offsprings using the best members. So the idea of keeping the best solution is that because the best targets are having some characteristics that we want to keep in the population. And then we generate the offspring is the generation of the offspring is to get the population closer to what we want and to also introduce diversity. So this is the basic idea. And here are some key concepts in this algorithm. So if you just watch the slides from here or watch the recording from here, you may think, okay, this is like some kind of biology course, but actually we are in a computer science course. So this graph is actually borrowed from some biology textbook. So because this algorithm is actually inspired by the biology concepts. So the concepts we are going to learn here are not the cells, these protein or nucleus, and we are going to use the chromosome and gene. So individual. So inside this population, so we are actually evolving the population generation by generation. So that's the basic idea, and inside each generation, we have a population of individuals, right? And these individuals are like the solutions or the targets we are trying to optimize, right? So the individuals in the population compete for resources and reproduce. That's a basic idea. And those individuals who are successful are calculated as fittest by the fitness function, then reproduce to create more offsprings than the filtered out ones. So we can keep the genes of the fittest parent and propagate and then we can propagate the fittest genes or the good characteristics from the parents and propagate these good characteristics throughout the generation. So, so that is why, because we may sometimes combine good genes of different chromosomes, right? So that is why sometimes and most likely the offsprings can be better than both parents. So that's the basic idea. And each chromosome is actually considered as an individual, and each gene here is actually some kind of characteristics of the chromosome. So it's like a part of the individual. So because we can generate, it's likely that we can generate offsprings which are better than their parents. So the quality of the entire population gets better and better throughout different generations, right? So the question here is, what do chromosomes correspond to according to the description here? Actually, I just mentioned the answer. So the answer is chromosomes are actually like the individuals here, right? So what are the genes here? What are the genes? So genes are actually the properties or characteristics of the individuals. So this is the idea here. And what is the population? So the population in terms of testing, what is the population? The testing is actually the set of chromosomes or the set of individuals or the test suite if we want to evolve the test cases. So this is actually the workflow of this genetic algorithm. It's actually very, very simple to implement. You can implement this algorithm with like within 100 lines of code in Python. So the basic idea is we initialize the population randomly. So for example, if we are trying to get a test suite, what we can do is we can initialize we can populate this test suite with a set of random test cases, right? We can randomly generate everything here. And then we can create offsprings with the members of the population. So what we can do is we select the parents and recombine them. So recombine them means we do crossover, like we select maybe the first half of a certain test case, and then we select the second half from another test case, and then we combine them together into a new test case. So this is how we do crossover. And after doing crossover, we may use use a small chance to randomly mutate the offspring we just generated. So this is to add some extra randomness or diversity to the population here. So after doing this offspring generation, then we can use a fitness function to calculate the survival population. So we have to specify a fixed size of the population. So we don't keep the population growing. We have to fix the size because we just want to keep the best genes here. And the survival function here is used for calculating the fitness of each individual candidate here. And then we use the fitness function to calculate a score and filter out the bad ones and only keep the good ones. And then we keep on this, we keep looping through this process until we set until the stopping criterion is reached, or maybe like we have run out of budget, or maybe certain number of generations have been generated, or if we have found the solution here. So this is a basic workflow. So here are some key things that we could take note for this workflow. So the first one is when we initialize the population, we can do random initialization. And this process is also called reproducing. And when we do the survival calculation, we use the fitness function. So you can see that the design of this fitness function is very important here. And the last one is we need to set some termination criterion for this algorithm. And normally we limit the number of generations we would like to try. So this is a basic idea of genetic algorithm. And although it may sound very cruel, like it's not, we are eliminating some bad things, bad individuals, but they are just test cases. They are not like humans or whatever, It's like we are just eliminating some test cases and keeping some good test cases here. So this is a genetic algorithm, and it actually works very, very well, not only in testing, but also some other problems, optimization problems. So for unit testing, actually genetic algorithm has been applied very, very successfully. And this evil suite is actually a unit testing generation framework for Java programs. So if you click on this, if you click on this link, you can get to this website. So it's actually a very, very successful unit test generation framework. You can use it to automatically generate unit tests for any given piece of Java code. So it has been developed. It was created in 2010, and it has soon dominated this field of doing unit testing. And by that time, like there were two groups of people. One of them is the Evil Suite group. They were promoting this genetic algorithm for creating unit tests automatically, and another group of people were trying to use, model-based testing. So remember when we learn system testing, system level of testing, we learned that we can model the behavior of the system, right? We can use some models of the systems to create test cases. And the other group was trying to use this model-based testing idea to create unit tests. And they were eventually defeated by this group. So genetic algorithm was kind of proven to be a very, very useful technique for doing unit test. And considering that it was created in 2010, it's actually a very, very young technique. Because comparing to all other techniques we are learning nowadays, like, it's a very young technique. Many techniques we are learning are actually older than you could imagine. Like for example, for neural networks, it was actually created. The idea was proposed in 1980s. Like by that time, the hardware was not powerful enough to train good models. So people don't take it seriously. But then as hardware evolves, it becomes more popular. So many techniques are very, very old. But this one is very, very young. And let's come back to the genetic algorithm. And genetic algorithm actually was also, the idea of this algorithm was also kind of reflected in the design of fuzzers, especially the American fuzzy lob we have learned. So actually, there are some differences in the process. So we can see that American fuzzy lob was trying to maintain a queue of seed inputs, right? This queue of seed input is actually somehow like the population, right? And it actually keeps growing this queue of inputs, and maintaining this queue of inputs and trying to make it better and better, right? This process of iteratively making the entire population better is similar to genetic algorithm, but there are some differences here. So the initial population or the initial seeds of these gray box father, whether it's AFL or mini-lob you are going to try in assignment 2, the initial seeds are not randomly generated. They are kind of provided by the users. So this is one difference. And the reason of using user-provided input is that because if we just purely randomly generate the initial things, we may take a very, very long time to fully optimize the population, right? If we can already get some good or high quality seeds or high quality population or high quality test cases, then it will give us like a performance boost during the start of the testing. So this is why one difference here. And another difference is like when we create offsprings or new test cases, it doesn't always do this kind of reproduction using two test cases. We can still mutate a single parent. Like in assignment 2, there are two types of mutation operators. One is called crossover, the other one is called havoc. Havoc is like purely randomly creating a new test input based on a given seed, right? But crossover means like we are trying to combine two seeds to create a new test case. So AFL doesn't always try to combine seeds. And another difference here is AFL doesn't try to kill certain population, so it doesn't discard any test input. Instead, it calculates the favored seeds. So it doesn't remove seeds, it just favors some seeds. So that's the difference here, but essentially the idea is similar. And the last thing here is like some of you have asked questions in the forum as well. So when should we? So it's like the father is running forever, right? If you don't manually stop it. Actually, that's the design. That's the desired behavior of fathers. So normally we just use the time as a stopping criteria here. So we don't use the number of generations to have. So we just use time here for termination. So for example, for AFL, we can specify that, okay, this father will just run for maybe 5 hours or 24 hours. So that's the last difference here. But the overall process and the overall idea is very, very similar. Sorry. And that's all for today's lecture. And before we finally end, let's have a quick recap of what we have learned today. So basically, we covered 3 different topics. And the first one is actually the basis of the other tool. So it's like we are trying to convert testing as a searching and optimization problem. The reason that testing could be converted or transformed as a searching problem is that we are trying to search from the infinite input space a suitable test suite, right? We are trying to find the suitable test cases from an infinite space. So that's why it could be considered as a searching problem. And why this searching problem could be further considered as an optimization problem, the reason is we can, because normally this input, sorry, this input space is infinite, and we can't exhaustively try out all the solutions to find the ideal target, right? So we have to use some budgets. We have to have some constraints, and since we cannot find the best solution here. We have to find the optimal solution that is the so-called best within all the candidates we can get from with our budget. Then this problem becomes an optimization problem. Since the problem of testing could be converted into searching and optimization problems, then we can apply algorithms that can deal with search and optimization problems to do testing, right? To create test cases. So in this way, we can apply some techniques like adaptive random testing, which is to basically to try out some seeds and then select the next candidates which are furthest away. And we can use some zone-based variations to further optimize this algorithm. So that's the first one. And the second one we learned today is a meta-heuristic algorithm, which is called genetic algorithm. And genetic algorithm is to actually optimize a population of individuals generation by generation. And we are introducing diversity into this population by reproducing offsprings with some parents in the population, right? And we are keeping the good genes or the good characteristics by using a fitness function to filter out some bad solutions. So that's the basic idea. And that's it for today's lecture. And thank you for coming.